Hello. Introduction to resonance. So I'm going to talk a little bit about magnetic fields first, and then I'm going to jump over and relate everything we've done with electrons to nuclei. Okay, light. Electromagnetic radiation. We typically only talk about the electro part, the electric field aspect of radiation, because that's what couples with the, or is in well, it couples with the oscillating electric dipole moment and causes transitions in vibrational, rotational, electronic, and so on. This is a completely different technique. NMR is a resonance technique, and that involves the resonance of the magnetic field with nuclear spin states or electric spin states if you're doing EPR. Okay, but let's jump to it. Light. What do we know about light? So light is a self-propagating wave of an E field and a B field. E electric, B magnetic. So how well the electric field of this light permeates through space is called epsilon 0. And then the permittivity in a medium, it's not light or not vacuum, is the dielectric constant, it's epsilon. But magnetic fields, however, also affect light. The magnetic aspect interacts with the magnetic B part of this light. So you'll have a B field, and B is equal to mu0 1 plus x h. This is not the Hamiltonian. And so this H is the magnetic field strength. This is like Maxwell's equations in like 5 seconds. And then, not really, this is a small introductory part, but whatever. So here you've got, this is the magnetic permeability. Of free space. Basically, how well magnetic fields can permeate through vacuum. And then this here, X, is called the magnetic susceptibility. If it's 0, then this term goes to 1, and your magnetic field is your magnetic permeability times the strength of your magnetic field. If it's greater than 1, you're going to increase the strength of the magnetic field, and if it's less than 1, you're going to, or less than 0, I should say, you're going to decrease the strength of the magnetic field. We won't do any of this, but I want to give you some context, specifically for the constants that you're going to be working with, and one of the coolest relationships I have ever seen. All right, so mu0 right here, the magnetic permeability, again, how well can a magnetic field permeate through free space? That's going to be dependent on the speed of light. So mu0 is equal to epsilon 0, oops, sorry, didn't think that was right, 1 over c squared epsilon 0, such that 1 over mu0 epsilon 0 is equal to c squared. That's pretty cool that relationship exists. That's just neat. So the permeability of free space of electric fields, the permeability of free space of magnetic fields. Awesome. Okay. So with that said, now I want to, well, I'll pause and erase. We're going to be jumping into using that magnetic susceptibility soon. So I wanted to give you an introduction. But let's do a comparison between the electron and the nuclei, with comparisons of the angular momentum, the magnitude of the angular momentum, the z component of that, and so on and so forth. Okay, electrons have intrinsic spin. That's been the name of the game lately. And so that angular momentum associated with the spin, the orbital spin, is designated with the quantum number L, and it has a magnitude of L times quantity L plus 1, square root that, h bar. Go team. We've done this a lot. Now we're going to, instead of me deriving all of that, know that you can do the exact same thing with nuclei. The difference here, this is the orbital quantum number, orbital angular momentum quantum number. Electrons also have the intrinsic quantum number S, okay? We are looking at the intrinsic quantum number I, in this case for nuclei. Okay, so this is actually better related to the and when you're thinking about it, the intrinsic spin s of the electron, but mathematically it actually works out that it follows the orbital angular momentum much better. So the magnitude of the angular momentum, any guesses? I times I plus 1 quantity 1/2 h bar. Go team. Hopefully you're now seeing the similarities. The z component is m sub l. The z component of the intrinsic spin of the nuclei, m sub I. The values of m sub l can go from negative L to minus L plus 1 to 0 to L minus 1 to L. And same thing, minus I to 0 to positive I. The other thing, the number of orientations that we can have is 2 L plus 1, because space is quantized, so you can either have m sub l is equal to minus 1, 0, or minus 1, 0, plus 1, so that would be 3. So if L equals 1, then this would be 2 times 1 plus 1 gives you 3 orientations. Likewise, 2I plus 1 gives you the number of orientations. Sweet. So we have a parallel between the orbital angular momentum of the electron and the intrinsic angular momentum of the nuclei. And we're going to combine those, or use what we've done time and time again. Guess what's coming? We're going to do this to the nuclei, and we're going to get nuclear states, energy states. And then we're going to get in resonance with those. Okay? Cool. I'm going to pause and erase. Don't look behind me yet. So you may know that not all nuclei can be seen in the NMR. We always look at proton or carbon-13. We don't necessarily, or we can't really look at carbon, carbon-12, and we can't look at some other nuclei. That's because intrinsic spin of the nuclei are not just plus or minus a half like electrons. They can be multiple things. So if we have, so the values of I, so this is again the spin of the nuclei. Here's the example. So for carbon-12 and oxygen-16, so both of those have even number of protons and neutrons, okay? So the total spin of the nuclei is going to be 0. Can't see that. But for hydrogen and nitrogen-14, the number of protons is odd, the number of neutrons is odd. You combine those together, and you're going to get an integer spin. Okay, that's actually much like a photon. A photon has integer spin. Electrons have half integer spin, and that's one of the problems about having electronic states, vibrational, rotational, all that, have transitions, and why we need the selection rules is because you have to get a integer spin value within the photon to transfer to a half integer spin of the electron. That's tricky. Okay, so we don't do this anymore. We could do that, but it's a lot harder. We're going to do this NMR. So this is the one that you're familiar with, carbon, so proton, NMR, as well as carbon-13. You may have done, some of you have done nitrogen. I've done lithium, phosphorus, fluorine, and those 3. And I've never done any of those. So it goes. My career is a long time. Okay, we'll see what happens soon. So how do we, so the integer spin, or sorry, the spin of these depends on the number of protons and the number of neutrons. So if you add number of protons plus number of neutrons, and if that equals an odd number, you have half integer spin. So 1/2, 3 halves, 5 halves, and so on. Okay, so when you add them together, so the number of protons plus the number of neutrons gives you an odd number. What that means, if you look in Atkins, it says if your protons are odd and this is even, half integer. If this is even and this is odd, half integer. So if one of these two is odd, if you add them together, you're guaranteed to get an odd number. So I just add them together, and then that tells you, or you just memorize it, that also helps. But that's where that comes from. Okay, for hydrogen, we have I for H1 equals 1/2. So that means that there are 2I plus 1 orientations which is 2 times 1/2 plus 1 gives me 2 orientations. And we're going to call these 2 orientations alpha and beta. Okay? You may have heard of spin flip. That's fine. But spin flips are flips between alpha states and beta states. Go team. All right, that's all I got to say about that. Okay, now we're going to talk about the energies of those 2 states, the alpha and the beta state. And when you're dealing with magnetic fields, the energy is equal to the magnetic moment times the vector of the magnetic moment dotted with the magnetic field. So this is the magnetic field, and it's in units of Tesla or Gauss. And so Tesla would be a T, Gauss would be a G. And Tesla, just to give you a sense, first of all, Tesla is equal to 1 kilogram per second squared amp. And I was curious, so I looked it up today. So a typical fridge magnet is about 5 millitesla or 50 Gauss. That's tiny. That's like 5 milligrams. That's not even a paper clip. That's like, if we were to equivalent that, equate that to mass. So 5 millitesla, but you can still feel it. So it tells you the kind of the strength of a Tesla, right? 1,000 times higher than that would be very strong. So the Earth's magnetic field is 31 microtesla. So this is Earth. Very, very, very weak. Okay, typical NMR, this is a 500 megahertz. Ours is a 400, by the way, is 12 Tesla. Huge, that's pretty big. Or as I like to say, big ass magnet. Huge. Okay, so that just gives you a sense of what Tesla is. So you take that Tesla, the strength of the magnetic field, dot it into the magnetic moment, which is, so this is the magnetic moment, and that equals, oh, no, I'm not going to go there yet. It equals a magnetic moment. Basically, the strength of the magnetic field across how much of the magnetic field you've actually gone through. And so that gives you the energy. Okay, to get the total energy of our system, you guessed it, I said total energy. This is a quantum class. Hamiltonian equals to minus mu operator. This is the magnetic moment operator dotted into the B field. Cool. And so the magnetic moment operator, this is what I wanted to go into, is equal to the, oh no, I think I have a mistake. Pause for a second and correct something. Sorry, thought I was missing a negative sign. We're good. That negative sign is supposed to be there. Okay, so we've got the magnetic moment operator. This is the quantum number I. Again, that's the operator of the angular momentum of the intrinsic spin. You've got the gyromagnetic ratio. So this is the gyromagnetic ratio, sometimes known as the magnetogyric ratio. Gyromagnetic is how I learned to say it, whatever. And this is nuclei specific. All right. And so what we want to do is we want to look specifically at, so you're going to have your big magnet, and you're going to have an, it's actually going to be this way. So, well, I think it's actually kind of sideways. So you're going to have a certain direction to your magnet or to your magnetic field. So we want to look at all of these energies specifically in one particular direction. That direction we're going to align with the Z component because we have I sub Z, which is going to give us to M sub I. And we've done everything with respect to the Z axis, and so that's what we're going to do now. So we're going to have the Hamiltonian in the z is equal to minus magnetic moment operator in the z direction, B0, which is the z direction B field. And that's going to equal minus gyromagnetic ratio B0 I operator in the z direction. Go team. So I'm going to pause and erase. So we have our total energy operator, gyromagnetic ratio B0, this is the magnetic field, and the z component of the angular momentum operator. Okay, so h psi equals e psi. From there, we get an energy of, specifically with the quantum number m sub I, is going to equal minus gyromagnetic ratio B0 h bar, because it's quantized m sub I, where this is your eigenvalue. So we've got quantized energy states associated with the spin intrinsic angular momentum of the nuclei. Yay! Say that 3 times fast. All right. So I'm going to simplify this into more useful experimental nomenclature. So this is equal to G sub I UN B0 M sub I. Cool. So my B0 and my M sub I are there, but I've put the other terms into these two. So let's talk about what these two are. So G sub I is equal to the nuclear G factor. This is experimentally determined because it contains this gyromagnetic ratio, and it equals mu n h bar over, or sorry, delta n, that's not delta, that's gamma, h bar over mu n, where mu n is the magneton, and that equals eh bar over 2 times the mass of the proton. Oh my gosh, that's a lot. Okay, go team. So we've got the charge associated with mass, and we don't use mass of a proton very much, but we're dealing with the nuclei here. Fun stuff. Okay, so we have all of that. This is what's important. That's our energy state. Go team. Now I should say that the G value is experimentally determined. I have a couple here. Actually, I'm just going to write them on the, I'll erase and write them on the board. Hello again. Okay, so just to compare some gyromagnetic ratios and the G factors. So we've got, so I've got proton here. So this is a unitless value. So I'm pretty sure it's a unitless value. Yes. So you've got 5.58, so 5, carbon 13, nitrogen 14, 5, 1, and practically a half. So you can see that it gets pretty small pretty quickly, but it starts, well, 5. And so nitrogen 14, by the way, has spin 1, or integer spin. The gyromagnetic ratio, however, so this is per 10 to the 7th, so this would be 26.75 times 10 to the minus 7 inverse Tesla inverse seconds. Sorry, times 10 to the 7th, and then you divide that out to get this value. And so 26, 6, and then 1. So proton is the one that has the highest strength. And this is going to be related to the intensity of the peaks. This is one of the reasons that proton NMR is much easier to use, especially for undergraduates. It's the one we always start you off with because it's just easier to see the data. Intensities are much higher. Cool. Okay. Well, that's actually the video I have for introducing you to magnetic fields and resonance. So this is intro to resonance. Things to keep in mind. There's an analogy kind of to electronic states, but we're going to get into some very strange, it's not an absorption technique. I'll leave it at that. It's not an absorption technique. It's a resonance technique. And I want you to know the difference between those two. The other thing to keep in mind is that we're going to be dealing with magnetic fields. And so some of the numbers won't make much sense just unless you have experience using magnetic fields. Cool. Okay. In the next video, I'm going to talk about the degeneracy lifting and what happens in the NMR, and then we'll move on to how the NMR works. Go team, that's all I have for today. Bye.